One of the very special features of systems of linear equations is that there is a general method to solve any such system. This method is called row reduction. In this video, I will show you the first steps of this method. Let's consider an example. Suppose we want to solve the following system of equations. Note that each equation involves at least two variables. Because of this, it is hard to see immediately what the solution is. Our aim is to simplify the system by reducing the number of variables in the equations. So how can we change the system without changing the solutions? Right, we can apply row operations. Let me show you how to do this in a structured way. First, we rewrite the system as an augmented matrix. To make the system simpler, we want to create zeros in this augmented matrix. We start at the first row and look at the first non-zero element. We will use row operations to make all the entries below this element equal to 0. We can do that as follows. First, add 2 times the first row to the second. Then, add the first row to the third, and then subtract the first row from the last. We then have obtained a row equivalent matrix. You see that the second row starts with 2 zeros, whereas the last 2 rows start with 1 zero. Before I continue, I reorder the rows such that the rows with more zeros at the beginning appear lower. I will explain later why we do that. We can reorder by interchanging the second and the last row. This is also a row operation. After reordering, look at the first non-zero element in the second row. As before, we make zeros below this element. We can do this by subtracting the second row from the third. Again, we want that rows with more zeros at the beginning appear lower in the matrix. We don't need to do any ordering for that, it is already the case. We go on to the third row and look at the first non-zero element there. Again, we use a row operation to make the entries below it equal to 0. Now we arrived at the following situation. If you look at the first non-zero element in each row, you see that they form a staircase pattern. We say that the augmented matrix is in echelon form. In fact, the word echelon derives from the Latin word scala, which means stairs. The first non-zero elements of the rows also have a special name. They are called pivots. To be precise, we say that the augmented matrix is in echelon form if the following holds. Each pivot occurs to the right of the pivot in the row above, and rows with only zeros are at the bottom. So why do we care about this echelon form? First, let me summarize what we did. We started with a system, put it in augmented matrix form, and applied row operations to get it in echelon form. This augmented matrix corresponds to a system that is equivalent to the original system and therefore has the same solutions. But it is easier to solve. The third equation tells right away that x3 equals -1. Then from the second equation it follows that x2 equals 3, and then the first equation tells us that x1 must be 9. And since row operations do not change the solution set, this is also the solution of the original system. You can check this yourself. The procedure that I showed you works in general to put any augmented matrix in echelon form.